Hello. In this video, I'd like to discuss a couple of topics that we didn't have time to cover in our previous discussion of acids and bases. You'll find these in slides numbers 3 and 5 in Acids and Bases Part 1 of the PowerPoint slide packet that was previously distributed. Okay. You recall that according to Lowry-Brunstad concept of an acid-base reaction, an acid is a proton donor and a base is a proton acceptor. And when an acid reacts with a base, the acid donates a proton, or hydrogen ion that is, to the base. However, the chemist G.N. Lewis, looking at this definition of acids and bases, was critical. He noted that in the Lowry-Brunstad concept, it's always a hydrogen ion coming from the acid that binds to an electron pair of the base. He noted that, chemically speaking, there are many other species that can bond to a base in an analogous fashion. Namely, there are species that have an empty valence orbital that can accept an electron pair from a base and bind to the base in that way. Here's an example. Borane, BH3, chemically bonds to ammonia. Borane has an empty orbital in its valence shell, and it meets up with an ammonia that has a lone electron pair in its valence shell. The two come close enough that the orbitals overlap, and basically the borane then accepts the electron pair from the ammonia, making a new covalent bond. Lewis argued that if we use the term acid-base reaction strictly for hydrogen ion bonding to an electron pair donating to a base, that's very limiting. He argues that the term acid-base reaction should apply to any species with an empty valence orbital that binds to a species with an electron pair in its valence orbital. So he recommends that the term acids and bases should be used in a broader sense, and he defines an acid and base as follows. An acid, according to Lewis, is any species that accepts an electron pair. A base is any species that donates an electron pair. Examples: one that we'd shown previously, BH3, reacts with NH3. The boron accepts an electron pair from the nitrogen, forming a new bond. The nitrogen donates an electron pair to the boron, forming a shared pair bond between the boron and the nitrogen. Thus, we'll refer to the BH3 as a Lewis acid and the NH3 as a Lewis base. The Lewis acid is any species that accepts electron pair, and the Lewis base is any species that donates electron pair. Here's another example. If we put a zinc plus 2 ion in water, the zinc plus 2 will spontaneously bind to 4 water molecules. It forms 4 covalent bonds to water molecules. This gives what's called a complex ion. Well, in that covalent bond forming process, the oxygen of each water is donating an electron pair to the central zinc plus 2 ion. Thus, the zinc plus 2 ion is accepting an electron pair from each of the waters, and each of the waters is donating an electron pair to the central zinc. So each of the waters is a Lewis base. Zinc plus 2 is the Lewis acid, and so forth. In general, Lewis base is any species with one or more lone electron pairs. Lewis acids include metal cations and molecules. Molecules containing aluminum and boron also can function as Lewis acids. These elements have an empty p orbital in the valence shell and can accept an electron pair. Generally speaking, Lewis acids are positive species or electron deficient species. Alright, it turns out that there is a relationship between the strength of an acid and the strength of its conjugate base. Let's consider any weak acid. It will of course have a conjugate base. Ka is the dissociation constant for the weak acid. Its conjugate base will also have base properties. It will be basic, and let's let the symbol Kb be the dissociation constant for the conjugate base. We learned in general chemistry that for a weak acid and its conjugate base, the mathematical product of the acid Ka and its conjugate base Kb is a fixed value, 1 times 10 to the minus 14 at 25 degrees, which you might remember is also the value of what we call Kw. That's the same equilibrium constant that results when water undergoes an acid-base reaction with itself. Now if you look at this mathematically, this again would be for a conjugate acid and its conjugate base. We can see that there's a general relationship. If we do something to increase the strength of the acid, the Ka value will increase. In order to keep the product Ka times Kb constant, the Kb of its conjugate base must correspondingly decrease. In other words, as Ka increases, Kb must decrease. Or put differently, if we do something to make an acid stronger, the strength of its conjugate base gets weaker. As acid strength increases, the strength of its conjugate base decreases. And here's an example. If we have a very strong acid, it would follow that its conjugate base should be very weak. And indeed, if you look at HCl, a very strong acid, its conjugate base is chloride ion. And chloride ion is an extraordinarily weak base. It's such a weak base it has no observed base properties. So HCl is very strong. Its conjugate base, chloride ion, is very weak. Here's a somewhat now different application. Look at the following acids. They're arranged in order of decreasing acid strength. The strongest acid is on the left, HCl, and the weak acid is CH4. Water is right in the middle. If we write down the conjugate base of each of these acids, we have chloride ion, hydroxide ion, OH minus, and CH3 minus. These conjugate bases, if we write them in order, we find that if placed in the same sequence, that is chloride ion, hydroxide ion, CH3 minus, that they will be arranged in order of increasing base strength. That is to say, chloride ion is the weakest base and the CH3 minus ion is the strongest base. Hydroxide, in terms of its strength, is right in the middle. So we note the relationship that if we have a series of acids going from strongest to weakest, that if we write down their conjugate bases in the same order, the order of acid strength goes in the opposite direction. It increases. Or put differently, in this series here, the conjugate base of HCl is a very weak base, chloride ion. The other end, the very weak acid CH4, its conjugate base, CH3 minus, is very strong base.